In this video, we'll look at the process of creating a linear graph, populating with values, and projecting future values based on past performance. A very simple example of predictive analytics. The example we're going to use is retirement savings. Let's say, for the sake of argument, we want to plan different strategies for saving retirement for the next 30 years or so. We'll start with a column for year, and I'm going to populate this with 2022. It's an integer value representing the year 2022. And for each year, we'll have a column containing a value for our contribution and the resulting balance after the contribution is made. Let's say for the first year, we're going to contribute $2,000. The balance at the end of that year, we can reasonably expect to be around $2,000. I'm going to use a formula to add. In this case, I'll simply make it equal to the value in the cell on the left. Notice when I'm in cell C2 and I type the equal sign to begin the formula and click on cell B2, it populates it with the letter B, the number 2, just like in Battleship. Column B, row 2. By hitting return, that formula, which you can see up here in the formula bar, is populated in the cell with the number equal 2,000. Now, the year after that will be 2023, and then 2024, etc., etc. Rather than populate this manually, which wouldn't take that long to do 30 rows, but rather than do this the hard way, I'm going to use another formula with a relative reference like this to populate cell A3 with the value of cell A2, the one just above, plus 1. Hitting return populates that cell with the value 2023, and if I copy that and then select the next 30 or so rows, pasting the value, you'll see that the successive years get populated automatically. 2023 and so on and so on. Each one of these cells is actually populated with a formula, and notice that the reference is a relative reference. That is to say, in cell A7, it refers to the cell above it, A6 plus 1. In cell 8, it refers to cell A7 plus 1, and so on and so on. That's the thing to remember with formulas in spreadsheet programs like this. By default, they are relative references. So if you copy that cell and paste it into another cell, it will refer to similar cells based on the new position of the cell. And that's handy here. It shows us the year values for the next 30 years or so. I'm going to use similar formulas to populate the contribution row. Let's say that cell B3, that's my contribution for 2023, will be equal to the value in the cell above it, unless I change that value to override it. Likewise, I will copy this, and in all of the cells below, I will paste it. And that means that each cell value in column B will be equal to the value of the cell above it. So if, for the sake of argument, I decide 10 years down the road to change my contribution value to 3,000 per year, and if I hard code that with a value like 3,000, hit enter, notice every value below that is also equal to 3,000. Now, in our balance column, for the second year, 2023, I'm going to use a similar formula to make this equal to the value of the balance from the previous year, just above, and I'm going to multiply that by a relative rate of return, or I'm going to hard code a rate of return of, let's say, 5%. Imagine the $2,000 I had invested in the previous year earned a 5% rate of return. I'm going to multiply it by 1.05, 100%, plus an additional 5%. Now, in addition to this, I'll put this in parentheses, in addition to this, I will also add plus the value of the cell to the left, B3. Hit return, and the value you see is populated with $4,100. That is the $2,000 contribution for the new year added to the $2,000 balance from the previous year with a 5% return. Notice that Google Sheets is suggesting that I fill all cells below with the same formula. And I can do this using that same relative reference. That is to say, each cell in column C will be calculated by multiplying the cell above by 1.05 and adding the value of the cell to the left. These are all relative references. So we end up with values over time that increase, partly from the contributions being added, partly from a rate of return on the value from the previous year. Very nice. Just to visualize this, I'm going to highlight the year and the balance. I'm holding the Shift key down while selecting each of those columns. And from this, I'll make a chart. Not bad. As you can see, the values over time increase on a curve. That's that 5% rate of return being projected into the future. That's very nice. What you might not see is right around year 10, that's year 2030, that the curve takes a bit of a sharp or a gradual increase. The curve that was projected to this point increases a bit. Let me change that $2,000 contribution to $3,000 there. I'll change it, say, $5,000. And that increases all successive values. As you can see now, this curve takes an uptick around here. And if around this point we increase that to $10,000, based on increased income, we can hope down the road see another visible break on these curves. This gradual curve, if I'd continued to project only $2,000 per year, would probably wind me up around here. In fact, if I want to see that for sure, at the end of our 30-year period, that taps out around $132,000. These increases over time give us a much higher balance at the end of the 30 years, based on those increased contributions. Now, as it stands now, I can make some modifications to the contribution amount over time, and we can project different strategies for long-term investment. However, we still have that 5% rate of return hard-coded into the formula. What I want to do is create a place where I can replace that value in a single place without modifying a formula in every single row to get an idea of what this would look like if the rate of return were better or worse. What I'm going to do is I'm going to create another column. Call this return. The data type for this is going to be a percentage. If I select format number, one of the options is %. I'm going to populate this initially with the number 5. 5%. Now, this value is stored in a single place in cell E2. In the initial formula in cell C3, I was multiplying the previous balance by 1.05. Instead of 1.05, I'm going to make that 1 plus the value in column E2. Now, that works here, but it causes a problem if I use that same formula in successive rows. The percentage doesn't get calculated because these are relative references. As you can see, cell E2 becomes cell E3, 4, 5, and so on. What we want is a hard-coded reference, a hard reference rather than a relative reference, so that I can change the value in column E2 and it'll be reflected in every calculation in column C. So, the way to use hard references rather than relative references in a spreadsheet program like this is to precede the column and the row reference with a $sign. $E, $2. That tells the program that in this formula, the row and column for E2 should not change if I copy this into another cell. So, copying this new version of my formula and pasting it into each successive value below does in fact add percentages for each one based on whatever this rate of return is. And now if you change that rate of return to 0, you'll see it's more or less linear. We have no curve because there's nothing being accumulated, because there is no compound return. A modest return like 1% turns this into a gradual curve. A dramatic return like 15% turns it into a very sharp upswing. Let's set this to say around 8%, which is a reasonable goal, nonetheless ambitious, and we'll leave the contribution values as they are. For the first 10 years or so, we're going to contribute $2,000. For another 10 years, we're going to contribute $5,000 a year and then increase that as we get closer to retirement to $10,000 a year, which is what gives us this upswing here. Now let's say, for the sake of argument, that our investment is not a savings account giving a guaranteed rate of return, but something with a more realistic variable rate of return, market-based. So we can predict that it might give us an 8% return, but in actual practice, we don't know until the end of the year what that value is actually going to be. So let's say, as we go on, as time passes, our balance gets reported to us at the end of the year. And at the end of the first year, our balance is slightly above 2,000 because we got a little bit of accumulated returns. It ended up being $2,058, say. I'm going to put that in bold, just so you can distinguish this value from something that's calculated in a projection. This is an actual value I got at the end of that first year of savings. And I predicted from that point that the $2,000 contribution for the next year and the assumed rate of return that my balance at the end of the next year would be in this range. But let's say it worked out to be slightly better than that, 45.89, a little bit higher. These numbers are recorded data from my end of year checking the balance. We have some good years, we have some bad years, some atrocious years, and then in other years it bounces back dramatically. These numbers are not projections, they are actual live recorded data. And it makes for a messier graph, but that's what reality looks like. Now, these values each reflect a certain rate of return from the previous year. Not this projection, but an actual rate of return. I'm going to use a formula to calculate what the actual rate of return for each one of these years was. I'm going to record that in this column here. I'll label this column Return Calc. That is to say, a calculated return. For the first year, there's nothing to record because there's no previous year's balance against which to compare the values. For this year and subsequent years, I'm going to record a percentage value. We format this again as a number %, and the calculation for the actual rate of return for the year 2023 will be equal to end of year balance equals cell to the left minus contribution amount for that year minus the previous year's balance, put all that in parentheses, and then divide it by the previous year's balance. And the rate of return for that year gets calculated at 25%, slightly better than we expected with the 8% calculation. If I copy this, paste it into the next year, we see a much better rate of return. In the subsequent year, a much lower rate of return, and the year after that, a negative rate of return, which is entirely possible. Considering we contributed $2,000 to this fund, and the resulting end balance is actually less than the previous year, that's a disastrously low bad year. Very nice, though. So what we can see is that in the good years, we had a maximum return of 59%. In the bad years, negative 37%, because the market fluctuates, and maybe my investments are really high risk, and I'm trying to go for big money. Now, these subsequent years, I'm not going to paste my rate of return yet, because I'm going to wait until I actually have live data to record. Let's say at the end of 2028, I had projected, based on an 8% rate of return from the previous year, that it would be something like 19,000, and it works out to be 19,005. Now, when I copy that formula from above, paste it here, you can see that my calculated rate of return is just slightly above 8%. The formula seems to be working. Now, in my projected years for the future, I am basing my rate of return on a hard reference to whatever the value is in cell E2. And I can play around with this 8%, increasing it or decreasing it, and see in the visualization, in the graph, what the resulting long-term projected balance would look like over time. What I'm going to do is, instead of using a hard-coded rate of return, I will now calculate this rate of return based on the average of the performance of the years that for which I actually have recorded data. Notice, as I say, I am not populating these until I actually get the recorded value for the end of the year. So at this point, I have 6 years worth of data and 6 years worth of calculated rate of return. If I were to average these together, I'll get an average rate of return based on past performance. And I'm going to replace this hard-coded 8% with that new calculated average. Simple enough to use a formula, equals average. As I start typing, notice the sort of IntelliSense autofill will show me different formulas that match that. And in this average, I'm going to calculate the average of all the values in column D from D3 and on down. Now, the years that don't have a calculated average yet will be ignored in the calculation, but when they get populated later, they will be incorporated into the average. So, we now have a single value in cell E2, which is referred to with a hard reference in each of these subsequent balance year calculations. So, based on these 6 years worth of data, there's a rate of return showing of 16%, which seems very nice, but it's only based on 6 years. So let's say we add a little bit more data in. The projection for the 7th year was around 24,000. I'm going to put that, let's say at the end of the year, it's a little bit less than that. Put that in bold. I will copy the formula for the rate of return in cell D8, paste it into D9, and you'll see, notice that the calculated average rate of return, currently at 16.3% for my previous 6 years, automatically drops down to 16% based on these 7 years worth of data. 14% return was good, but it was less than the previous 16.3 projection. So every time this fails to meet that rate of return, it modifies it slightly down. Let's say there was a very bad year the next year, 28,000, with a $5,000 contribution. That represented a very slight loss, negative 2.8%. It happens. And my overall average rate of return has dropped to 13%. Still respectable because of several good years, but it does over time get modified, as you can see. And if you pay attention to this graph, as I change these, you'll see that the long-term projection for the end balance, which is the end game with this, it modifies up and down. It goes up and down based on projections. And the more years I have recorded, the more accurate this calculated rate of return becomes, because it's based not on 6 years worth of data, but on 8 or 10. And over time, this rate of return gets matched more closely to what has happened in the past. So we have a shorter and shorter future projection based on a longer and longer past rate of return. Now, giant caveat. This graph will not tell the future. It will only project future values based on the assumption that the future performs the way the past did. That's not a guarantee, but this type of dynamically calculated rate of return is more valuable in predicting values than it would be with a hard-coded guess. Because this, everything in bold here, can be assumed to be live data, and the more live data we have, the more useful information we have about past performance. On a side note, I can tell you I have used a similar method for my own retirement planning in a spreadsheet I've been using for more than 15 years, and I have older versions of that that have contained long-term projections based on certain assumptions for my contributions and a calculated rate of return. And over time, it's turned out to be different from what I expected it to be 10 years ago, but not radically so. This type of predictive analytic allows us to make projections and from them modify our strategy. Say, increase our contribution value. If we're not getting the rate of return we want, we can up that from 5,000 to, say, 8. And then 12. Which, with these formulas, automatically increases subsequent values and automatically factors that into the balance calculation. So, this is an example of how simple predictive analytics can allow us to plan for the future, to tweak our strategy based on different assumptions, most notably among which is that future performance will be like the past.